So I think it is an important question. Is a software program running on a computer more like a building or a factory? I think it's more like a factory. A software program takes input, warehouses intermediate results, and produces output. So in this way, Garland and Shaw's architectural styles can be thought of as describing the layout of a factory plant. In fact, the layout of the factory, that is analogous to the structure of the software, has a big impact on the efficiency of the factory. But then so does the machinery. So if a software program is like a factory, and the architectural styles are like the layout of the factory, then what is analogous to the machinery of the factory? I think it's the computations. Now, over the last 40 years, we have thought quite holistically about the overarching structure of software. We've thought quite a bit about individual algorithms, like the shortest path between two vertices in the graph, but we've tended to think of computations as a huge ball of yarn with individual threads, known as algorithms. Now, one advance over this was developed very incidentally by Phil Colella. He's at Lawrence Berkeley National Labs. And in a relatively informal presentation to the DARPA High Performance Computing Systems Group, he talked that all simulations in physical sciences could be broken down to 7, he said, algorithms, I would say computational families: structured grids, unstructured grids, fast Fourier transform, dense and sparse linear algebra, particles, and Monte Carlo. So when you hear this, it sounds like, perhaps these high-performance computing people have a big advance on how to think about holistic software. Perhaps they can help us with parallel computing. Well, a little investigation shows that the high-performance computing approach to architecting software begins with a computation, and then, however complex that computation is, for structure simply puts a Quonset hut over it. Technically, they've even got a term for this, which is known as a monolithic architecture. So I'm afraid they can't help us much there. Nevertheless, Colella got us off to a good start, and beginning in 2004, we, researchers at Berkeley Power Lab, went on from his work to identify 13 fundamental computational families. So you'll see a variety of application areas such as embedded computing, spec benchmarks, databases, and so forth. You'll also see individual applications like health, image processing, speech, music, and computer browser. And then what you'll see is a set of computations, all in all 13 computations, which we felt was sufficient to span the computations across these broad areas. Red here in an individual cell indicates that this computation is quite prevalent. So for example, graph algorithms are quite prevalent in embedded computing. Orange means somewhat less so. So for example, graphical models show up somewhat less in databases. Green, even less so. So backtrack, branch, and bound are only partially showing up in games. And blue shows that these computations hardly show up at all. These 13 computational families, called dwarves, were published in the Berkeley Review shortly thereafter. So now we do have a description, a concise description of the machinery of the factory. So how can we pull this all together? We would like to be able to architect software with a single integrated vocabulary of design. We'd like that vocabulary to be sufficiently formal to be meaningful and yet flexible enough to incorporate the diverse set of design decisions associated with a sophisticated software program. So how can we do that? We're looking for a single vocabulary for architecting software. We'd like to be able to architect software within a single vocabulary of design, and we'd like that to be flexible and formal. So we found the most useful mechanism for incorporating this was going back to Alexander's pattern language. So again, a pattern describes a recurrent problem with a generalizable solution. Alexander described 253 patterns ranging at all levels of design, and he described a pattern language as an organized way of tackling an architectural problem using patterns. So to go a little more detail and to give an example, so one of his groups of patterns addresses the overall layout of a group of buildings, the height, the number of these buildings, the entrances of the site, the main parking areas, and lines of movement through the complex. Now, the fundamental problem that he's trying to address with these set of patterns is one that's very familiar with us. We go to a particular address, we're looking for a particular office or a particular shop in a shopping center, and we're often confused, looking linearly through each individual shop. The solution that he says is to lay out the set of entrances to form a family. They all form a group, they're all visible together from a single vantage point, and they're broadly similar, something that looks like this. So what are the value of patterns for software? Well, they're flexible enough to incorporate both the mathematical and the artistic elements of design. Giving names improves communication, gives a common vocabulary among developers. It improves the documentation. It also aids the design process in a number of ways. For beginners, it's often they're unclear about how to get started. It gives them a palette of choices with which to get started. For veterans, they often wonder, when am I ever finished? The palette says this is a set of design decisions you need to consider. It articulates very big design decisions very succinctly and codifies good design practices. Moreover, each pattern distills and disseminates a vast amount of experience. These also facilitate, in addition to design, the processes of maintenance, restructuring, and refactoring. So with these notion of patterns, we can refine the definition of software architecture. A software architecture describes the overall structure of a software system as a hierarchical assemblage of computational components chosen from among the 13 computational patterns, composed by structural components chosen from among the 10 structural patterns. Now, there are two key elements of this definition. The first is that it addresses simultaneously computation and structure, but also that it gives a finite palette for each. It gives 13 computational patterns and 10 structural patterns. And although it certainly seemed like a bold notion when we first got started on this, we really do stand here and believe that all computational programs can be broken down and described with these 13 computational patterns and 10 structural patterns. So taking from the top, we identify the software structure using the 10 structural patterns. These describe the structure of our software, but they don't describe what is computed. The analogy here, again, is the layout of a factory plant. Then we identify the key computations from among our 13 computational patterns. This is analogous to the machinery of the factory. We go back and forth among these hierarchically until we have a complete software architecture of something that, say, is the large vocabulary continuous speech recognition system, which I describe here, which is analogous to the design of an entire manufacturing plant. Now, when I first thought of this notion of software as factory, I was immediately excited, and I ran over to the engineering library thinking they must have given a lot of thought as to how to actually build and optimize factories. In fact, they do, and they consider things which are very relevant to parallel computing, like scheduling, latency, throughput, workflow, resource management, capacity, and so forth. So again, we have a set of 10 structural patterns and 13 computational patterns. We go back and forth between these two, analogous to both the layout and the machinery of the factory. Now note that a pattern language is more than just patterns. So there's Christopher Alexander. Oftentimes I feel if you ever meet him, he's such a influential man. He kind of gets his way into your mind. He becomes your conscience forever. And I kind of hear him saying a pattern language is an organized way of tackling an architecture using patterns. It's not a pattern language. It's not just a set of patterns. So our goal here was to provide a single integrated pattern language which goes all the way from application through high-level architecture, which I've described today with structural and computational patterns, down into parallel algorithm strategy patterns, implementation in software, and execution targets. This is our pattern language as a whole, consisting of less than 50 patterns. If we look at where this began, there are a set of 13 computational patterns, 13 dwarfs from the Berkeley View paper. There were Garland and Shaw's architectural styles generalized into our structural patterns. And all this sits on top of Tim Matson of Intel's book, Patterns for Parallel Programming. So let's review the key points of today's talk. First, software is like a factory. A software program takes as input, warehouses intermediate results, and produces output, and this raises the relevant issues of scheduling, resource allocation, and workflow. Second, a software architecture must include both computation and structure. Our 10 structural patterns are 13 computational patterns. A pattern language is more than just patterns. A pattern language is an organized way of tackling an entire architectural problem using patterns, analogous to our tackling an entire software application. Here's our pattern language overview. Here's our entire pattern language. And this is me presenting our pattern language in 2010 to Christopher Alexander, and it's been a very enjoyable afternoon discussing. We got quite a lot of interesting questions and engagement from him on our pattern language. In subsequent lectures, we'll be going through in more detail our entire pattern language.
Hey, I hope you liked this video. If you haven't seen our other videos on the Intel Software YouTube channel, remember to subscribe, and don't forget to leave us a comment. Tell us what other material you'd like to see, and chat with other enthusiasts who watch our shows. See you next time.